In this section, we'll talk about characters and strings. As we've already seen, the character type can hold values that represent characters. These values are basically integers that map to a character set, like the ASCII character set. And we've also seen that strings are sequences of characters. C++ supports two types of strings, C-style strings and C++ strings. So we'll first look at the CC-type library. This is a library of very simple but very useful functions that work with characters. For example, we can test characters to see if they're uppercase or lowercase, numeric, alphanumeric, punctuation, and more. We can also convert characters between lower and uppercase. After we learn about the CC-type functions, we'll talk about strings. As I said earlier, you can think of strings as a sequence of characters. So far, we've only used string literals, which were represented as a sequence of characters inside double quotes. I'll discuss both C-style strings and C++ strings in this section, and give you the basics of using each. However, you should be using C++ strings in modern C++. I think you'll understand why at the end of this section. First, we'll see what C-style strings are and how they're represented in memory. Then we'll see how to work with C-style strings using some of the string functions available in the CString and CStandardLib libraries. Then we'll learn about C++ strings. C++ strings are objects, just like our vectors were, and they're used using an object-oriented style of programming. In this section, we'll learn how to declare, initialize, assign, compare, and use some of the other C++ string methods. Methods are functions that work with objects. So let's look at C-style strings first in the next video. In this video, we'll talk about the functions that we can use with characters. The CC-type library includes very simple and very useful functions that allow the testing of characters for various properties, as well as the conversion of characters from upper to lower or lower to uppercase. In order to use these functions, you must include CC-type. The functions all expect a single character. In the case of the testing functions, they evaluate to true or false, and the conversion functions return the converted character. Let's see some of these functions. This table contains some of the functions in CC-type that allow for testing of characters. You call the function and pass in the character you wish to test in the parentheses. The function then evaluates to true or false depending on whether the character has the property you're testing or not. IsAlpha tests to see if the character is a letter, either uppercase or lowercase, and evaluates to true if it is or false otherwise. IsAlNum tests to see if the character is a letter or a digit. IsDigit tests to see if the character is a digit. IsLower tests to see if the character is a lowercase letter. IsPrint tests to see if the character is a printable character. IsPunct tests to see if the character is a punctuation character. IsUpper tests to see if the character is an uppercase letter. And IsSpace tests to see if the character is a white space character. There are a few other functions in CC-type that I haven't listed in the table. You can refer to the C++ docs for those. Now let's see the conversion functions. The two character conversion functions are toLower and toUpper. toLower evaluates the lowercase equivalent of the character passed in, and toUpper the uppercase equivalent. If these functions can't perform the conversion, then the functions simply evaluate to the character that was passed in. As you can see, these functions are very handy. They're also extremely efficient. We'll use these functions in the next few videos when we talk more about strings. In the next video, we'll learn about C-style strings. I'll see you there. In this video, we'll learn about C-style strings. C-style strings are about as simple as it gets. They're a sequence of characters stored contiguously in memory. They're implemented as an array of characters, so you can access individual characters using the array subscript syntax that we've already learned. How do you know where the sequence of characters ends? C-style strings use a sentinel value that marks the end of the string. The null character is used, which is equivalent to the integer 0. So, C-style strings are often referred to as zero or null terminated strings. We've been using C-style strings all along in this course. We've used them mainly in our output statements as string literals. Recall that string literals are sequences of characters enclosed in double quotes. These string literals are constant, so we can't change them, just like we can't change integer literals. Even though we don't explicitly provide a null character at the end of the string literal, C++ inserts one for us. That's the way the end of string is handled. Let's see an example of a string literal and how it's stored in memory. Here's a real simple example that shows how C-style strings are stored in memory. In this case, we have a C-style string literal containing the sequence of characters C++ is fun. These characters are stored in a contiguous block of memory that can be accessed as an array. Notice that C++ is fun has exactly 10 characters, but the compiler allocated 11 characters for the array because it needed space for the null character at the end. Literals are great and very useful, but we more often than not need to create string variables. Let's see how we can create C-style string variables. In this example, we're declaring an array and initializing it to Frank, using initializer list syntax as we've been doing with integers and other types. Notice that the C++ compiler will allocate 6 characters for this array, since it needs to terminate the string with the null character. Also notice that the size of the array is fixed, so if I wanted to add a Y to Frank and create Frankie, I couldn't without having some potential problems, since the new string would not be null terminated. You won't get a compiler error or even a warning. In fact, in this case, my name sub 5 is still within the array bounds. Let's see another example. In this example, we are explicitly asking the compiler to allocate 8 characters for the character array. And we're initializing it to Frank. In this case, it will initialize the array with Frank, and the rest of the space will be zeroed out with null characters. In this case, if I wanted to change the character at index 5, which is that first null character, to a lowercase y, it would be just fine, since the string now contains Frankie and is still null terminated. Let's see another example. In this example, we ask the compiler to allocate an array of 8 characters and we don't initialize them. This could be very problematic, because if you use this array as a string, all C-style string functions expect to find a null character. And here there may or may not be one. We really don't know what the data in the array is. Suppose we wanted to display the string now. How do you think this would happen? How do you think C-style strings are displayed? Well, in this case, we start at the first element of the array and we iterate through the array. At every character, we see if it's the null character. If it is, we stop since we reached the end of the string. If it's not, we print the character and then we move to the next character. In this case, we don't know what's going to happen. We might see a null right away, or we might not see a null for a very long time. In the meantime, I'm printing stuff to the screen. Some of the stuff may not even be displayable since some characters are control characters. You might think we can initialize C-style strings using the assignment operator, just like we have with other types, but this won't work. If we try to assign the C-style literal Frank to my name, we get a compiler error because that's not the way C-style strings work. Array names and literals evaluate to their location in memory, so we're effectively assigning one location to another, which is illegal. Think of this as saying assign 10 to 12. It doesn't make sense and the compiler won't allow it. In order to assign one string to another, we need to use a function called string copy that copies the C-style literal Frank to the myname array. There are lots of C-style functions that C++ brings in from the C programming language. Let's see a few of them. The C-string library contains many functions that work with C-style strings. These functions are used to copy, concatenate, compare, search, get the length of a string, and many more. They all rely on one common factor, that the sequence of characters they're working on is terminated with a null character. If you're using C-style strings, you must be very aware of this. For example, suppose you have a C-style string and you want to determine its length. Well, let's say we have Frank. Since no length information is stored with the string, only the characters in the array, the only way to determine the length is to start counting at the first array element, and then increment along until you see the null character. So in the case of Frank, we would look at the F, Increment 1, look at the R, 2, the A, 3, the N, 4, the K, 5. Then we see a null character and we stop. Now we know that the length is 5. But if that null character is not there, we keep going and we keep counting. So the result will very likely be incorrect. Even worse, if you're copying one string into another and the string you're copying isn't null terminated, you'll very likely exceed the bounds of the target string and very likely cause a program crash. This all sounds pretty ominous, but in fact, we've been programming in C and C++ using C-style strings for a very long time, and we've gotten pretty good at understanding these issues. But wouldn't it be great if we didn't have to worry about these issues at all? That's where C++ strings come in. We'll talk about them later in this section. Here are a few examples that use the C-style string functions. You typically have a function and you pass into the function the name of the string or the string literal or both. We'll talk about functions in detail shortly, but conceptually they're really easy to understand. For example, if I'm a function and my job is to return the color of a crayon passed to me, then all I need from you is the crayon. So you call me and send me the crayon and I'll return red, green, blue, and so forth. That's the idea, and here it's the same. If you want to know the length of the string, pass in the string to the strlen function, and it returns the string's length. Here are just a few examples that copy, concatenate, and compare strings. C++ also has another library called cstdlib that contains functions that convert strings to other types. For example, if I have a string with the digits 1 and 2, I can convert that to the integer 12. Sometimes these are real useful functions. However, all of these functions rely on the same thing. They're all working with null terminated strings. If you're using C-style strings, you have to be very aware of that. Well, that completes this video. In the next video, we'll head over to the IDE and we'll write some examples using C-style strings. In this video, we'll go over some examples of using C-style strings. First thing you'll notice is I'm including C-string. I need to include that header file for the C-style string functions, and I'm also including CC_type. That's because I'm going to use some of the character-based functions in this example. Okay, so I'm using namespace standard, and I've declared 4 C-style string variables, which are really just arrays of characters on lines 9 through 12. First name, last name, full name, and temp. And I've made them to be pretty big, 20, 20, 50, and 50. That should allow us to put stuff in there without exceeding the bounds. Okay, so the first thing we'll do is, notice here, first name is uninitialized. They're actually all uninitialized. Let's display first name. This is a real problem because we've never initialized that array. So it's very likely we're going to get garbage. So let's run this. And by the way, I'm in the section 10 workspace in the C-style strings project. So let me run this. And there you can see the garbage right up here. You can see it right in there. What displays is, who knows, right? Whatever characters happen to be in those locations. You might get lucky and the null character might be in the first location, in which case nothing will print. But more often than not, you'll get garbage like this. And this is a real common symptom. And whether you're displaying to the console or inside a window in Microsoft Windows or X window, and you see something that displays like that on a button or up here on a title bar or something, that's a classic symptom of uninitialized string. Let me comment that out. We don't want uninitialized strings. Now, obviously, we'd want to initialize these guys just like that, or to a string if we want. So let me just go ahead and initialize all of them, which is really the best practice. Okay, so now they're all initialized. So the first thing we'll do is I'll uncomment these lines here. And this is nothing we haven't seen before. Pretty straightforward, right? Enter your first name, and we're using the extraction operator to read our first name into that variable first name, which is the array. So whatever I type in, I'm just going to use my name in these examples. Frank will be stored into first name, and it'll be F-R-A-N-K, and then the null character will automatically be put in there for us. Same thing with last name. Okay, so again, nothing we haven't seen before. Now here, let's talk about these two lines. In this case, let me grab my marker real quick. In this case, we're saying, hello, first name. Now, this will be replaced with the value of first name. What's the value of first name? Well, at this point, I have Frank in there. And remember, this is 20 big here. But in this case, let's just say I've got that. That's the null character. So how do we determine the value of first name? Well, we start here. Do we see a null? No. We move over. Do we see a null? No. And we keep going until we see that null. At that point, that's what's returned. So this will display Frank. That's really what's going on when we're displaying these C-style variables. Okay. So it's going to say, hello, Frank, your first name has, and then we see this function right here, the strlen, or the string length function. A function is nothing more than a request for somebody else to do something for you. And we'll write functions really soon, I think in the next section. So in this case, I'm calling the strlen function. I'm passing in that array of characters, Frank. So what's it going to do? It's going to do the same thing we just did here, right? Let me clean this up a little bit, and we'll walk through this again. So in this case, how does the string length determine the length of that name? Well, you start here. Is that a null? No. That's 1. Is that a null? No. That's 2. How about this guy? Nope. That's 3. The N? Nope. The K? That's 5. Now we see the null. The length is 5. That's what's being returned here. Now, strlen doesn't return an integer. It doesn't really return an unsigned integer. It returns a type called size t. And I haven't talked about that yet, but I'm going to now. Size t really is an unsigned integer. It could be an unsigned long. You really don't know what it is based on your system. That's the whole point. We really should be using size t because regardless of what system you're on, this will work. You can be sure it will be unsigned though, right? Because it doesn't make sense to have negative sizes for strings or negative sizes for loop variables and things like that typically. So from this point forward, I'm going to start using size t where appropriate rather than int or unsigned. It's the more correct way of doing it. Okay, so that'll return 5. So this will display, hello, Frank, your first name has 5 characters. And your last name, same idea. It'll print out my last name here, and my last name has 11 characters, so it should display 11 characters. Okay, so let's run this example. My first name is Frank, and I'll put in my last name, Metropolis. And it says, hello, Frank, your first name has 5 characters, and your last name, Metropolis, has 11 characters. Exactly what we expect. Now, everything I'm talking about in this video is totally dependent on that guy right there. If for whatever reason those null characters or that null character is not there, you can imagine, right? We're going to keep counting until we hit one, which may be, 1,000 characters down the line in memory. Typically, you don't have to worry about it when you use these functions, strlen, cin, strcat, like we'll see down here. They handle that for you. But if you're working with strings on your own and you're processing characters and moving characters around, you've got to be aware that you need to null terminate your strings. Otherwise, you're going to run into problems. All right, let me clear this up real quick. And let's do another example down here. I'll uncomment this piece of code out and we'll talk about that real quick. So what do we have now? Well, we have Frank in first name, right? So first name is Frank. I just typed it in, and I'll type it in again in the next example. What we're doing here is we're copying using the string copy function. We're copying first name to full name. This is the way it works. It's going from this right argument to the left one, not the other way around. This is confusing sometimes for students. So I'm copying first name into full name. So again, here was first name, and it had Frank in it. And over here is full name. Again, this is first name, and this is full name. How does it copy? Well, one character at a time. It's going to copy the F, the R, the A, the N, the K, and it's going to keep copying until it hits that null character. At that point, it copies the null character and it stops. Okay. So at this point, full name will have Frank followed by the null character. The strcat function is the concatenate function. In this case, what I'm doing is I'm adding a space. You can see the space right there in double quotes. I'm adding the space to full name. So now it's putting a space here, right in there, and then it's putting the null character. So at this point, that's going to be Frank followed by a space. I'll just use that underscore to denote the space. Then I'm doing another string cat. And what I'm doing now is I'm concatenating. Again, this goes this way. I'm concatenating the last name to the full name. So now I'm putting in my last name here. And it will also put in the null character at the end. And then I'm just displaying it. Okay. So notice what we're doing here. What we're doing is we're basically building up full name from first name and last name using strcat or string cat. Let's run this, and what I'll do here is I'll say, again, my first name is Frank, and my last name is Metropolis. Hello, Frank. All that's the same. And then it says here, your full name is Frank Metropolis. Notice how it concatenated the Frank, the space, and the Metropolis into one. So full name now contains that string. Okay, so let's do another example. I'm going to comment all of this out so we're fresh every time. And in this example here, this is an example that shows you one of the behaviors of the cin extraction operator here. What I'm doing here is I'm prompting the user, me in this case, for my full name, and I'm going to enter the full name, and then I'm going to display the full name. Okay, so let me run that, and I'm just going to say my full name is Frank Metropolis. But now when I try to display my full name, notice I only get Frank. That's the normal behavior for that extraction operator. It's reading in FRANK space, that's a white space, so it stops. That's it. Okay. Sometimes you want to be able to read the entire name, right? The whole line. So this is what we'll do in these next few lines here. In this case, again, I'm prompting enter your full name, but now I'm using cin's getLine function. This works again with C-style strings. So in this case, I'm providing the name of that C-style string, or that array name here is full name, and a limit. This is how many characters maximum you're going to read. So I'm saying cin getLine. So this will stop either at 50 if you reach the max, or when the user presses enter. So in this case, it's going to read the whole name, right? So let me run that again, and I'll say Frank Metropolis again, and press enter. You can see that the full name now is the first name and the last name. So it's reading the entire line. Now let me do a couple of more examples. Let's do a comparison example here. In this case, remember, full name will have my full name in it, Frank Metropolis. And what I'm doing that, I'm copying that to temp. Temp, if you recall, I'll scroll up real quick. Temp is another array of characters, pretty big, nice 50 size, so my name will definitely fit in there. And when I say big size, my name will fit in there. That's one of the things you always have to worry about when you're working with C-style strings. You've always got to be sure that you've got enough storage. If you don't have enough storage, you're going to have a problem because you're going to run over the bounds and probably clobber some other memory location with something. Okay, so again, let's assume that I've typed in my name, and now I'm going to copy my name to temp. Then I want to compare those two. They should be the same, right? Because I just copied it to another variable name. Well, we can use the string compare function. We pass in the two strings that we want to compare, in this case, temp and full name. And if we get back a 0, that means that they're the same. If we don't get back a 0, that means they're not the same. So in this example, I expect to get back a 0. So let me run this real quick, and I'll type in my full name. They are the same. Frank Metropolis and Frank Metropolis are the same because it's the same string. So I did get back the 0. Okay. So now let's modify that string, and then we'll compare it again. So what we'll do this time is we'll use a for loop, and I'll uncomment this code out real quick. And you'll notice what we're doing. We're going from I equals 0, and notice I'm using size t here instead of int or unsigned. This is the better way to do it, the more correct way to do it. So I'm going from I equals 0, while I is less than the string length of the full name. Okay? Again, string length is going to return however many characters are in there. I want to be sure I'm going less than that because remember, we're going from 0 to the size minus 1. And I'm incrementing I by 1 each time. Then I'm using one of the character functions. I'm saying full name sub I. That's the specific character, right? So it's going to be F, R, A, N, K, and so forth. If it's an alpha character, right, a letter, then I'm going to convert that letter to uppercase and put it right back where it was. So now my name will be all capitalized. Okay, so let's run that. And I'll type in my name with mixed upper and lowercase. You can see here that it compared them and they're the same. And now my name is all uppercase because I used the toUpper function. So now let's compare those two now. Obviously they're not the same, right? Because I just made one a little bit different. So let's do this. Let's comment all of this out and walk through it. And so what's going on here? I'm comparing temp and full name. They're not the same anymore, right? Full name is now all uppercase and temp is not. So I'm going to compare them, and it's going to say, are they the same or are they different? Now I expect this to be different because this will not be equal to 0. So how does this work with the 0? Well, if the two strings are the same, and that's character by character lexically, the string compare function will return a 0. Otherwise, it'll return a negative number or a positive number depending on which of the strings is larger. Right? So in this case, I'm comparing them temp and full name, and then full name and temp so you can see the result. So let's run this. So again, I'll use my name and press enter. So as you can see, the two strings are now different. And the string compare function will return 0 if the two strings are the same. You can see here that we're comparing two different strings. It returns less than 0 if the first string lexically comes before the second string, or return greater than 0 if the first string lexically comes after the second string. Okay, so that completes this video. This gives you a little bit of insight as how to use C-style strings and their functions. What we'll do next is we'll talk about C++ strings. In this video, we'll learn about C++ strings. Standard string is a class in the C++ Standard Template Library, or STL. We could do an entire course on just the STL, and that course would be very long and complex. So in this video, I'll only talk about the major elements of the C++ string class. In order to use C++ strings, you must include the string header file. Strings are in the standard namespace, so in order to use them without using namespace standard, you must prefix them with standard and the scope resolution operator. This is also true for the standard string methods that work with C++ strings. Like C-style strings, C++ strings are stored contiguously in memory. However, unlike C-style strings, which are fixed in size, C++ strings are dynamic and can grow and shrink as needed at runtime. C++ strings work with the stream insertion and extraction operators, just like most other types in C++. The C++ string class provides a rich set of methods or functions that allow us to manipulate strings easily. Chances are that if you need to do something with a string, that functionality is already there for you without having to rewrite it from scratch. C++ strings also work with most of the operators that we're used to for assigning, comparing, and so forth. This is a huge advantage over C-style strings, since C-style strings don't work well with those operators. Even though C++ strings are preferred in most cases, sometimes you need to use C-style strings. Maybe you're interfacing with a library that's been optimized for C-style strings. Well, in this use case, you can still use C++ strings and take advantage of them. And when you need to, you can easily convert the C++ string into a C-style string and back again. Like vectors, C++ strings are safer since they provide methods that can bounds check and allow you to find errors in your code so you can fix them before your program goes into production. Let's see how we can declare and initialize C++ strings. In all the examples in this video, I'm assuming that the string header file has been included and that we're using the standard namespace. Here you can see 6 examples of declaration and initialization of C++ strings. There are other ways as well using constructor and assignment syntax, but I'm mainly using the initializer syntax in this video. In the first example, we declare S1 as a string. Notice that the string type is lowercase. Unlike C-style strings, C++ strings are always initialized. In this case, S1 is initialized to an empty string. No garbage in memory to have to worry about. In the second example, I'm declaring and initializing S2 to the string Frank. Notice that Frank is a C-style literal. That's okay. It will be converted to a C++ string. In the third example, S3 is initialized from S2. So a copy of S2 is created. S2 and S3 will both be Frank, but different Franks in different areas of memory. In the fourth example, I'm declaring and initializing S4 from Frank, but I'm only using the first 3 characters of the string Frank. So S4 will be initialized to the string FRA. In the fifth example, I'm initializing S5 from S3, which is Frank. But notice the 2 integers that follow the S3 in the initializer. The first integer is the starting index, and the second is the length. So in this case, we initialize S5 with the 2 characters at index 0 and 1 from S3. So S5 will be initialized to FR. Finally, we can initialize a string to a specific number of a specific character. In this case, 3 X's. Note that this uses constructor syntax with the parentheses instead of the curlies. Now that we've declared some strings, let's see how we can assign other values to them. With C++ strings, you can use the assignment operator. This feels much more natural than having to use the string copy function like we would have to in C-style strings. In this example, I've declared S1 and it's empty. Then I can assign the C-style literal C++ rocks to S1. Pretty cool and pretty easy. S1 will grow dynamically as needed. In the second example, I've declared S2 and initialized it to hello. Then I assign S1 to S2. In this case, S2 will no longer contain hello. It will contain a copy of S1, C++ rocks. Let's see how we can concatenate strings together. Concatenation of strings just means building up a string from two other strings. We can use the plus operator to concatenate C++ strings. In this example, I created two strings, part 1, which is C++, and part 2, which is powerful. Then I have an empty string sentence. Notice that I'm assigning to sentence the concatenated result of part 1 plus a space plus part 2 plus a space plus language. If I displayed sentence now, it would display C++ is a powerful language. Notice that the last example on the slide will not compile. This is because we have two C-style literals, and you can't concatenate C-style literals. It only works for C++ strings. A combination of C++ strings and C-style strings is okay though, as we saw in the previous assignments. Just like we did with vectors, we can use the same operators to access string elements. In this case, the elements of a string are characters, so we can use the subscript operator as well as the @ method. Remember, the @ method performs bounds checking, so if you go over bounds, you'll get an exception which you can fix. Let's see how we can display string characters one at a time. In this example, we have a string S1 initialized to Frank. We can use the range-based for loop to display the string characters. In this case, FRANK, and the null character will be displayed. Pretty much what you expected, right? Notice that the type of the loop variable is char in this case. What do you think will happen if we change that to integer? In this case, I've changed it to integer. Is this what you expected? We told the compiler to use an integer, and that's exactly what it's doing. So instead of displaying the character value of each element in the string, it's displaying the integer value that represents those characters. So in this case, 70, 114, 97, 110, 107, and 0, which represent FRANK and, of course, the null character. These are the ASCII codes for those characters. Comparing C++ strings couldn't be any easier or more intuitive. We use the same equality and relational operators that we've been using all along. We're comparing two string objects, so they'll be compared character by character, and their character values will be compared lexically. So a capital A is less than a capital Z, and a capital A is less than a lowercase a. That's because the capital letters come before the lowercase letters in the ASCII table. We can't use these operators on two C-style literals, but we can use them in the following cases. If we have two C++ strings, if we have one C++ string and a C-style literal, or if we have one C++ string and one C-style string. Let's see some examples. Here we're defining 5 C++ string variables, S1 through S5, and then we perform some comparison operations and see the results. Of course, you would normally use these Boolean expressions in an if statement or looping conditional expressions. In the first example, we check to see if S1 is equal to S5. This is true since they both contain the string apple. S1 equals S2 is false since S1 is apple and S2 is banana. How about S1 not equal to S2? This is true since apple is not equal to banana. In the case of S1 less than S2, this is also true since apple comes before banana lexically in the ASCII table. S2 greater than S1 is also true since banana comes before apple lexically. Notice that banana has an uppercase B, whereas apple has a lowercase a. S4 less than S5 is false since apple with a lowercase does not come before apple with an uppercase. And then finally, A1 equal apple is true because they're the same. Notice in this case, apple is a C-style string literal. The C++ string class has a rich set of very useful methods, too many methods to cover in detail in this video. I encourage you to study the C++ string class since it's going to be a class that you'll use often, and it's important that you know what it provides so you don't reinvent the wheel when you need to solve a problem. The substring method extracts a substring from a C++ string. It doesn't change the string, it simply returns the substring, and you can do whatever you want with it. In this case, I'm simply displaying it, but you can easily assign it to a string variable. Here I've initialized s1 to this is a string. The first example takes a substring of this string starting at index 0 and including exactly 4 characters. If there are less than 4 characters left in the original string, then all the remaining characters are included. In this case, the substring is the first word in the string, this. In the second example, we return the substring starting at index 5 and include 2 characters. That's the substring is. Finally, the last example starts at index 10 and includes 4 characters. This will return the substring test. Let's see how we can search a string for another. The C++ string class has a very handy method named find. Find works with characters and strings. It expects a string or character and returns the index or position of the beginning of that string or character in the original string. So if we have a string s1 that's initialized to this is a test, and we want to find the string this, we'd get back a 0 since this starts at index 0. In the second example, we're looking for the string is. In this case, it would return 2 since the first is starts at index 2. In the third example, we're finding the string test and we get back a 10. In the fourth example, we're searching for a single character, the lowercase e, which is found at index 11. In the fifth example, we use a variant of the method that also allows the index where you want to start the search from. In this case, I want to find the is substring again, but I want to start at index 4, so this time it finds the is that's located at index 5. Finally, what happens if the string or character we want to find just isn't there? Well, in this case, the method returns an end position, which means no position information available. You can check for this value in an if statement, and if true, you know what you were searching for wasn't there. Very easy, very powerful. There's also an rfind method that starts searching from the end of the string to the beginning of the string. We can also remove characters from a C++ string using the erase and clear methods. For the erase method, you provide the starting index and how many characters to delete. The clear method deletes all the characters in the string, so the string becomes the empty string. We've seen a lot of string methods, and you can see how powerful this class is. Let's look at one more useful method and one more useful operator that are commonly used. The method is the length method. It returns the number of characters currently in the string object. In this example, s1 is Frank, so s1.length will return a 5. This is so easy and something that's impossible to do with C-style strings since they don't contain size information. The operator I wanted to cover is the compound concatenation assignment operator. In this case, s1 is Frank, and I can say s1 plus equals James. And James will be concatenated to Frank, and the entire result string will be assigned back to s1. This is really handy and works very much the same way that the compound assignment operators worked with integers and doubles and so forth. There are also many more methods in the C++ string class for you to discover as you study C++. Okay, there's one more thing I'd like to talk about before we end this video. Input with C++ strings. C++ strings work great with input and output streams. As you've seen, inserting C++ string variables to an output stream like cout is pretty easy and works just like we've been doing all along. Extracting a C++ string from an input stream like cin also works the same way we expect. However, there's one issue that's also true for C-style strings. Suppose we've defined s1 as a C++ string, and we extract a string from cin as usual. Now, suppose I type in hello space there. When I display s1, I will only see hello. The there was not extracted. This is because the extraction operator stops when it sees white space. In many cases, we want to read an entire line of text up to when the user presses enter. For example, I want the string to be hello there. Suppose I asked you to enter your full name. I want to be able to read William Smith, not just William. In this case, we can use the getLine function. The getLine function has a couple of variants. The first variant expects two elements inside the parentheses. The first element is the input stream. In this case, we're using cin, which defaults to the keyboard. The second element is the name of the C++ string where you want the text that the user enters stored. That's it, very easy. In the example, I'm saying getLine cin S1. Now everything the user types is stored into S1. GetLine stops reading when it sees the new line. It doesn't include the new line in the string, it just discards it. The other variant of getLine has another element in the parentheses. The first two are the same as before, the input stream and the C++ string variable name. The third is called the delimiter. This is the character that you want getLine to stop reading input at. So as long as the user doesn't enter this character, everything will be stored in the string variable. Once the delimiter is seen, it's not included in the string variable and it's discarded. In the last example, I'm using a lowercase x as the delimiter. So if I type this is x, then the string stored in S1 will be this is, and the x is discarded. Well, we've covered a lot of material in this video, and there's much more in the string class to learn. But this gives you a good starting point so you can use the C++ string class effectively. Also, you've now been introduced to object-oriented programming with both vectors and strings. Pretty soon we'll be developing our own classes, which is pretty cool. That completes this video. Please play with the string class, create examples, assign, delete, display, and try out some of the methods in this video. It won't take long before you're really comfortable working with C++ strings. In this video, I'd like to go over using the C++ string class and some examples there. So I'm in the Section 10 workspace in the CPP strings project. Now, remember, the string class is a class. So when we create strings in this case, here you see I'm creating 8 strings from S0 to S7 on lines 9 to 16. These are objects. We'll talk about exactly what objects are in the world of object-oriented programming in a future video. But we are using object-oriented programming here to work with these C++ string objects. Okay, it's important that you include the string library. Otherwise, you'll get a lot of compiler errors, and I'm using the standard namespace. First thing is, let's declare and initialize some of these string objects. Here I'm declaring S0 through S7. You can see S0, I'm just saying string S0. It's important to understand that with classes and objects in this case, S0 is an object. I am getting an initialized object. There's not going to be any garbage in there. And we'll display that in a second just so you can see what that looks like. Then I'm declaring other string objects here. So S1 is being initialized to Apple, S2 to banana, S3 to kiwi, S4 to apple, and so forth. S5 is being initialized to S1. Well, S1 is Apple. So a copy of that string is going to be put into S5. So S5 is going to be its own version of Apple. So if I change S1, it's not going to affect S5. There's also a couple of other initializers. There's actually a bunch of initializers and constructor style initializers, a whole bunch of examples that you can use, but I'm just sticking to the commonly used ones in modern C++. In this case, S6 is S1. I'm initializing it from S1, which is Apple, but I'm only using a part of it. I'm starting at index 0 and I want 3 characters. So it's only going to be initialized to the string APP. And then in this case, S7, I'm initializing that string to 10x characters. Notice the x is in single quotes here, so that's a character. And also notice that I'm using parentheses here and not curlies. This is a constructor style initialization, and that's the one that works with this example. Before we look at the initialization values, let's look at this right here. Notice that I declared that string object S0. If this had been the example that we saw using C-style strings and we never initialized it, you remember we saw all that garbage, you're not going to get that here. So if I display S0, you won't see anything because it's empty. And if I ask S0, what's your length? This is a method, this is an object, and this is what object-oriented programming is all about. I'm asking the S0 object, in other words, this string right here, hey, what's your length? And it's going to return its length. In this case, I expect back a 0 because it's an empty string. So let me run this. And you can see that nothing printed out because the string is empty. And I get back a 0, which says that the string has no length. It's empty. So you can see that it is being initialized. That's really important with objects. Okay, I'm going to comment that out. And then let's look at some of these initialization examples. I've just initialized those objects right up here where I declared them. Now I'm just going to display them. And you can see that we're getting exactly what we expected here. Let me scroll that up just a little bit. So S1 is apple, S2 is banana, then I've got kiwi, apple with a lowercase a, apple, and app, that's that 3, the initializer where we only wanted the first 3 characters. And then I've got 10 X's. Okay, so you can see really powerful, really easy way to initialize these string objects. So now let's comment this out again and work with some of the operators and methods of the string class. In this case, I'm comparing. If you recall, using C-style strings, we had to use the strcmp, or the string compare function, pass in 2 strings and get back either 0 or a positive value or a negative value, and then we'd have to check things like that. Well, here we can just use the operators that we're used to. And I'm using the bool alpha IO manipulator here just so it displays the words true and false. And you can see I've got a whole bunch of examples, and it's actually easier to run it than to read all that code. But you can see here that I'm comparing apple with apple, and I get back true. I'm comparing apple with banana, I get back false. Then I'm asking, is apple not equal to banana? That's true because they're not equal. Is apple less than banana? True because the capital A comes before the capital B in the ASCII table. What about banana greater than apple? Yes, again, I just flipped the sign and flipped the strings. What about apple with a lowercase a? Is that less than apple with an uppercase a? It is not, because the uppercase characters come before the lowercase characters in the ASCII table. And then the last one I'm using is right here, where I'm actually comparing an object, S1, with a C-style string literal apple. And that works perfectly fine, because what happens is this string literal right here gets converted to an object, and then we're doing object-to-object comparison. So that's true. Remember, it's doing character by character comparison. Okay, so real familiar, real intuitive, very easy to use. So let me comment that out. And let's do assignment. If you recall, with the C-style strings, we had to do strcpy, or string copy. Using C++ string objects, we just use the assignment operator, just like we're used to. So they feel like they're really part of the language, just like you would with integers and doubles and characters and so forth. So in this case, I'm assigning watermelon to S1. Okay. Whatever was in S1 before is now gone. Okay, I've overwritten it with watermelon. And then I'm outputting S1 is now, and obviously I expect back watermelon. When I say assign S1, well, S1 is watermelon to S2, I'm going to get a copy of that watermelon object, right? So I'm not going to, they're not pointing to the same watermelon. I'm going to get 2 copies that are individual. So if I change S1, it won't affect S2 and vice versa. And if I display S2, I also expect watermelon here. Okay. Here I'm saying S3 is Frank, so I'm assigning the string Frank to S3, and that should also display Frank. Now, once I've assigned these strings, I can manipulate them. So in this case, I can say change the 0th character in S3. Well, that's the F in Frank right here. Change that to a capital C. And notice single quotes because I'm changing a character. So I'm saying assign the capital C to the first element of that string, right? The one at the 0 index. So this would change it to crank, which will print out CRANK. I can also use the at method. Again, this is the whole idea of object-oriented programming. I'm saying, hey, S3, change the character at position 0 to a capital P. So when I display that, it should display prank. Let's run that and double check. So you can see here that S1 is watermelon, S2 is watermelon, S3 is Frank, and then I'm changing the first letter of Frank to crank, to C, sorry, and displaying crank, and then I'm changing it to a P and displaying prank. All right, I'll comment this out, and let's look at concatenation. I'll compare this to the C-style string where we had to use the string cat function, strcat, to concatenate 2 strings. Here, we could just simply use the plus operator. And in this case, I'm saying assign watermelon to S3. Okay, that's easy. But now I'm saying S3 equals S5. Well, S5 is apple, and S2 is banana, and juice. So I'm concatenating these 1, 2, 3, 4 strings together. by simply using the plus operator. The plus operator is considered overloaded. That means it works with integers, it works with doubles, and in this case, it works with string objects. Okay. So what we're going to do here is we're going to say apple and banana juice and assign that to S3. So in this case, watermelon is gone. We're overriding that. And then when we display S3, it should say apple and banana juice. All right, so let me run that quickly. And there you go. S3 is now apple and banana juice, just like we expect. If you try something like this, you're going to get a compiler error. The problem here is that we've got a C style string literal and another C style string literal and the plus operator. C style strings don't work with the plus operator. If you wanted to do something like this, you would have to use strcat and concatenate them together. In this case, you're going to get a compiler error saying something about, I don't know what to do with these two character arrays and this binary operator. Okay, so keep that in mind. If you're trying to use the plus operator, you've got to use it on at least one of the objects. Notice over here, we're using an object and a C-style string literal. That's okay because it'll convert. But when you've got two C-style string literals like this, it doesn't know what to do. Let's move on and talk about looping. In this case, we're going to use a for loop to loop through a string. Okay. Remember, a string is simply a collection, right? A bunch of characters. So we can easily loop through them. And we'll loop through them two different ways. First, we'll use a regular for loop, and then we'll use the range-based for loop. In this case, I'm assigning apple to S1, just so we have something to start with right here. And I'm initializing I to 0. Notice that the type of I is size t. This is really the proper way to do this. It's always going to be a non-negative number, right? Because we're looping through a string. Now, if you've got looping variables that need to go negative, you don't want to use size t. You just want to use a regular integer or something that's signed. But in these kinds of examples, size t is the proper type to use. So I'm initializing I to 0, and I'm going to loop while I is less than the string's length. Remember, we're going from 0 to the length minus 1. So in this case, I'm asking the S1 object, what's your length? And it's returning 5 because it's apple. So I'm going to loop 0, 1, 2, 3, 4, and then I'm going to stop. And as you see, I'm incrementing 1 each time. So every time through the loop, all I'm doing is just simply outputting that character at the ith location. So cout s1.at_i. I could use array subscript syntax. They both work. The .at method does bounds checking. The subscript method does not. So when I run this, I should see apple print out across the screen. And there it is. I'm just displaying it one letter at a time. I can also do this using the range-based for loop, in which case I'm just saying for every character C in S1, output it. Right? So it's going to go A, P, P, L, E, stop. So in this case, I see apple twice now, right? Once for the for loop and once for the range-based for loop. You can see some of these are very, very intuitive and easy to use. There's a couple left. Let's talk about substring here. This one, again, is very intuitive. Suppose S1 this is a test. I've just assigned that string to S1. And I want the substring that starts at 0 and is 4 long. So it's going to go THIS, right? The capital T is index 0. So that's going to return the word this, or the string this. In the second substring example, I'm starting at index 5, which is 0, 1, 2, 3, 4, 5. So it's starting at the I and is, and I want 2 characters. So it's grabbing this is right there. And that's what it's returning. And then the last one, I'm starting at index 10, which is the lowercase t in test, and I just want 4 back, and it's giving me test. So you can see it's very, very easy. And of course, all these, you can see here, it's displaying this is a test. All these are hard-coded, but you can certainly use variables for these integers and loop through in loops and grab pieces of substrings, and you can do a lot of really cool stuff. We can erase characters. In this example, I'm saying S1. Again, I'm assigning this is a test to it, and I'm erasing from S1. Again, notice the object-oriented style. Think of this almost as you're asking the S1 object, right? Because notice it's S1 dot. So you're saying the erase method is going to execute on that object, S1. Because we could have S2.erase, S8.erase, anything.erase, right? But in this case, it's happening on S1, which is, this is a test right here. So what I'm saying here is erase starting at 0 and erase 5 characters. So it's going to erase the capital T, the H, the I, the S, and the space. When I display that, S1 is now just the is a test part. I got rid of the this and the space from the beginning. All right, let's do a couple of more. The get line is a little bit different from the get line that we saw with C strings. If you remember with C strings, we said C in dot get line, and we had a length. Well, we're not worried about a length here because the C++ string class handles lengths for us. So it looks a little different, but it's the same basic effect. Here I've got a new string that I'm declaring called full name, and I'm initializing it to empty. I'm asking the user to enter their full name, and then I'm using the getLine function here, and I'm passing in where I want to get the input from, in this case the keyboard or cin, and where I want to store the result, full name. This will get an entire line up until I press enter. So, and then I just display the name. So in this case, if I run this and type my name, notice full name is Frank Metropolis, my entire name. It doesn't stop at the space the same way that the extraction operator does. The last thing we'll do is we'll look at the find method, which is a real handy method. So in this case, here's the secret word. The secret word is boo. That's the string. And I've got a word variable here, which is a string object. I'm asking the user to enter the word to find. The idea is they're going to type one of these words in here, right? And I'm going to tell them where that word is in the string, what position it begins at. So if I typed in the, I'm saying, hey, S1, again, the S1 object, find that word within you. So it's going to find the word the within it, and it's going to return 0 because it starts at the 0 index right there. That's the T. Again, I'm using a size T for the type because it's always going to be right 0 or greater or an error. And I'll talk about the error in a second. So at this point, I'm looking for that word in the string, and position holds its position whether it was found or not. How do I know whether it was found or not? I need to see if the position returned was that value, right? String end position, no position. So in this case, if the position I got back is not equal to that, then I found it. So I'm simply going to display found word at position, whatever. Otherwise, it wasn't found. So let's run this. And remember, the string is, the secret word is boo. So I'm going to run this and search for boo. And it says I found it at position 19. Let's run it again, and we'll use the word secret this time. It found it at position 4, and you can see there it is, right there at position 4. And we could try to find something that's not there, like hello, and it says hello, not found. Okay, so let me wrap up this video now. You have all the elements you need for the challenge that's coming up next. You could certainly try the challenge using C-style strings and then C++ strings, but I'm just going to do it using C++ strings because we really should be using C++ strings going forward. All right, so head off to the challenge. Hello, welcome to the Section 10 challenge. In this challenge, what I'm asking you to do is to create a substitution cipher program. This is really straightforward, but it'll give you some experience using the C++ string class. Now, there's an easy way to do this and a not so easy way to do this. I'm not going to tell you what the easy way to do this is because I want you to learn and try to figure it out on your own. Let me talk about the challenge. A simple, very old method of sending messages is the substitution cipher. I remember using this as a kid with some of my friends. We used to have something called a secret decoder ring. And the idea is you have a message, and then you look at every character in that message and you replace it with the character on the ring. So for example, every time you see a lowercase a, it gets replaced with a capital X. Or every time you see a lowercase b, it gets replaced with a capital Z, and so forth. So it's called the substitution cipher. It's really a straightforward cipher. It's not a very secure cipher at all, but it's a fun cipher to do. So here's the idea. I want you to write a program that asks the user to enter a secret message. That'll be a string. And then I want you to encrypt that message using the substitution cipher and display the encrypted message. Then take that encrypted message and decrypt it back to the original message. Okay? You can use two strings for your substitution. You can have one string for the alphabet. And let me write this here for you. That way you can maybe understand a little bit better. So let's say you have one string, which is the alphabet. And this string contains all the characters that you want to substitute. So for example, let's say we've got A, B, C, and so forth, and capital A, capital B, capital C. Okay. Then I've got another string called the key. And you can name these anything you like. And the idea here is that for every character up in the alphabet string, you're going to have a character in the key string that'll substitute it. So if I want to substitute that lowercase a for an X, it'll be here. And let's say that the B gets a Z and the C gets a Q, and then this uppercase A gets a lowercase, let's say Z, a lowercase q, and a lowercase d. It doesn't really matter what you replace them with. So now the idea is really straightforward. Whenever you see the secret message, let's say the secret message is ABC. You look in the alphabet, you look for that little a, you find it in position 0. Then you go to the key, look in position 0, and whatever's there, you replace it. You do the same thing with lowercase b. It's going to be replaced with the Z. And you do the same thing with the lowercase c, it'll replace it with a Q. Okay, obviously you just keep going down the string, whatever you find, you replace. So that would be my original message. This is now my encrypted message. How would I decrypt the message? You do the same thing, just the other way around. You look in the key for an X. I find it at position 0, so I go to position 0 in my alphabet, and I grab the little a. Again, I look for the Z, it's in position 1. There's my B in position 1. And then my Q is going to be in position 3. Position 2. And it gives me my C. So there you go. Really, really straightforward to do. Make the cipher stronger if you wish. This is a really weak cipher. Right now, it's only substituting the letters. And let me scroll down here just a little bit to show you what I'm giving you to start with. You can see what I'm giving you to start with. I'm giving you an alphabet, which is a string of all the lowercase and uppercase letters. I kept these in order just to make it easier to debug. And then you've got the key. Those are the substitutions. So for every one of these letters, there is an equivalent letter here that we're going to substitute. So for example, whenever we see a lowercase a in our message, we're going to substitute it with a capital X. Whenever I see a capital Z, I'm going to substitute it with a lowercase r. That's for encryption. And then for decryption, you just read the encrypted string and you go the other way around. So if you see a capital X in your encrypted string, you'll replace it with a lowercase a to decrypt it. That's it. Really straightforward. As I said, I'm only using letters here. I'm not dealing with numbers or spaces. You can be as creative as you want with that. There's a lot of ways to make this a lot stronger and just have fun doing it. Remember, I'm writing this right here on line 28. Remember, the less code you write, the less code you have to test. You reuse existing functionality in the libraries. Use the code that's in the string class. Don't try to create all this on your own. Remember the KISS principle. Keep this as simple as you can. Reuse as much as you can. And that makes your program very likely a lot more correct than it will be if you try to do everything on your own. Remember, those library functions and methods that we've used, they've been tested and they've been debugged for years and years, so they're pretty solid. So reuse those. So let me give you a sample run so that you can see what to expect. So I'm going to run this, and you can see here, enter your secret message, and I'll say, I'll meet you at Billy's house at 10 a.m. Okay, now I'll press enter. And it says encrypting message, and here's the encrypted message. You can see it's replacing characters. It's pretty obvious what's going on here, right? You can see the capital I in I'll is being replaced with a lowercase j. The apostrophe is not being replaced at all because I'm only dealing with letters. The lowercase l is being replaced with the capital D, you can see here. So you can see going across that's your encrypted message. Then I'm taking that encrypted message and decrypting it, just doing the opposite I just did, and I got back the same message I started with. Okay, so you can see it's pretty easy. So my secret message would be, this is my secret message. There's the encrypted message. Okay, you can see the third character here is an I. which is being replaced by a capital J. And you can see the I again right here in the is, and there's the capital J again. Okay, so have fun, like I said, and make it stronger. That's what I like to do. Learn and play around with ideas that you may have to make this stronger. It's a lot of fun to try. Okay, so when you're done, I'll see you over in the solution, and I'll show you my solution. Welcome back. I hope you enjoyed the Cypher challenge, and I hope you were successful with it. And I hope you extended it even further. If you did, post it on the forum. Share what you did. That's pretty fun stuff. Okay, so what do we need? First thing we need to do is ask the user to enter a secret message, right? So let's do that first. Let's knock that out before we even start writing any other code. So we need a string object, and we can call that string object secret message. And we'll initialize it. That's what the user is going to type in. Okay. So I'm going to say cout, enter a secret message. And we'll leave it just like that. And let me fix that typo. And you know what? Let me use proper English here. Enter your secret message. Now the user is going to enter their message, and we need to read it. It's potentially more than one word, so we can't just use cin and extraction operator. We're going to use getLine. And I want to get a line of text from cin, and I want to store it in secret message. Okay, so now at this point, secret message, that string object, will contain whatever the user typed in. Perfect. So we want to encrypt that string. Well, I need to store the encrypted message somewhere, right? So let's create another string object, and we'll call it encrypted message. And we'll initialize that as well. That's going to hold the encrypted message once we finish encrypting it. But at this point, it's just simply empty. So we'll do a little output statement here just so we can see some processing. And we'll say something like encrypting message. And we'll put an end line at the end. All right, so now we start to process. What do we need to do? Well, there's a lot of different ways to do this. There's the easy way and the harder way. Let's talk about the harder way first. Suppose that the message is Frank. That's the secret message. Well, I need to iterate through that string. Obviously, I need to look at the F, the R, the A, the N, the K. I've got to do that no matter what, because I've got to look at every single character. Well, what I could do is I could read the first character, that's the F. Then I can loop through this array here, looking for that F. And when I find it, I need to know what position it's in. So I could have a counter that's counting up, right? So that when I start at 0 and then I go to the next one, eventually it's going to find it and I've got a position. That's the hard way. That's not the way I want to do it. Remember, the string class has a method in it called find. So if I want to find that character F, it's going to return the position of F, or it's going to return no position. That's really all I care about. Okay, so that's the way I'm going to solve this problem. Less code is better. So let's solve this. So right here, we're about to encrypt the message. Now we need to iterate through the secret message, one character at a time. So I'm going to use a range-based for loop here. It's perfect for this. So I'm going to say for every character C in my secret message. So now in the loop, I have access to C, which represents the current character I'm looking at in my secret message, right? So I'm going to call the find method in the alphabet string. I'm going to ask the alphabet string to find C, right? So if C is F, it's going to find that lowercase f and return its position. Now that position's type is size t, just like we mentioned before. That's an unsigned integer that's really dependent on your platform. This will work everywhere. We'll call it position, and I'm going to ask the alphabet string, or the alphabet object, to find that character in itself. If it finds it, we're good. We're going to substitute it with the equivalent character at the same position in key. If it doesn't find it, then we're just going to process that character as is. It's not one of these. So I'm not going to substitute it. I'm just going to use it. All right, so what do we need? We need an if statement. We're going to say if the position is not equal to no position, What does that mean? That means we found it, right? Let's do the else. And I'll just use a block else in case we need to add some code later. Now, if we didn't find it in here, we're not going to substitute. We're just going to use the character as is, right? So I'm going to say encrypted message plus equals C. Just add the character as is to the encrypted message. We're not going to substitute it. Now, what if we do need to substitute it? Let's go back here again. We need a new character, right? We need the character in the key. So let's create a variable called new character, and we can initialize this variable to the character in the string at that position, the key string, right? So we have position already. So we can ask, again, we can ask the key string to give us the variable at that position. And we can initialize it to that. So now we've got the new character that we want to substitute. And what do? We simply say encrypted message plus equals new character. That's it. That should be all the code we need. Now let's just output the encrypted message. So the encrypted message would be the encrypted message. All right, so let's run this. This is the first half. This is just the encryption side. But you can see the code is really easy to understand, very straightforward. So let's run it. And let's say this is a test. And that's the encrypted message right there. Okay, now let's do a simple test case. We know that we're going to replace the lowercase a. You can see it right here. Oops, let me use my pen real quick. You can see that we're going to replace the lowercase a with an uppercase X. And it's obviously the capital Z with an R. So a good test case would be A, Z, 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 and we expect back X, 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 R, R, R. Right? That's the encrypted. So let's try that out. So we'll do 3 lowercase a's and 3 uppercase z's. A, Z, Z, Z. And as I said, what we expect back is X, 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 lowercase 3 r's. That's exactly what we want. Okay, so it looks like we're in the ballpark. Now, obviously, you would have to test a lot better than this, but that's a good example of a simple test case that tells you you're definitely on track. I'll erase this, and let's try a couple more. Let's try meet me at Bill's house. Now, in this case, you see we have an apostrophe. We're not going to handle that apostrophe, right? We're not substituting, so we're just going to print it out as is. So I expect to see that apostrophe in the encrypted string in the same position. So you can see here, there it is right there. So that's correct. All right, so that's the encrypted message. Now let's decrypt the message. Same idea, right? We're just going the other way. We need a string object for the decrypted message. And we'll initialize that to an empty string as well. We'll say cout. Let's do another new line here, and we'll say decrypting message. All right, so now let's do the code again. What are we doing this time? Well, this time we're looping through the encrypted message, right? Grabbing those characters, finding them in the key, and substituting them back in the alphabet. All right, so let's do it. It's the same exact idea, except we're going backwards here. So for every character, let's call it C, in the encrypted message this time, for every character in there, we're doing exactly the same thing. The position is we're going to ask the key this time to find that character. And then if the position is not equal to no position, then we found it. Right? The else part means just handle it as is. So let's handle that part real easy. So this time we're going to save this to the decrypted message, right? So decrypted message plus equals C. In this case, we did find it. So we want to get a new character again, just like we did before. There's my new character. And I want to initialize it to, this time, not the key, but the alphabets dot at position. So give me the character at the same position, but in the alphabet string. And I'll initialize it to that. And then here we'll just say decrypted message plus equals new char. Awesome. That's it. Our string should be decrypted at this point. And what we'll do here is we'll just say cout. Put another new line here in front. Decrypted message, and I'll fix that typo in a second. In this case, it would be decrypted message followed by a new line. Okay, let's try this out. Hopefully we get back what we started with, right? So enter your secret message. This is a test. I'm encrypting first. That's the encrypted message right here. Then I'm decrypting and I'm getting back this is a test. Perfect. Let's try a couple more. Meet me at Bill's house at, let's say, 12:30 p.m. Okay, this is a good test case because, well, maybe Nil's house, not Bill's house. Meet me at Nil's house. You see we have an apostrophe. We have the 1, the 2, the colon, and the 3 and the 0. We're not handling those since they're not letters. Okay? So we should see those characters as is in the encrypted string. So let's try that. There you go. There's the apostrophe. There's the 12, the colon, the 30, just as we expected. And then when we decrypt the message, we get back, meet me at Nil's house at 12:30 p.m. Okay. Now, suppose we wanted to make this a little better, not a lot better, but a little better. Let's deal with those spaces, right? I want to fill up those spaces with something. So what we could do is we could come up here to my alphabet, and I can insert a space right at the beginning. That's a space character. Now, what am I going to replace the space character with? Anything I want that's not already in here. Let's say one of those characters, a left bracket. That's fine, but now we've got to deal with the left bracket, right? So let's put the left bracket up here, and we're going to replace that with a space because we've got to go both ways or it's not going to work. All right, so now we're going to handle spaces. At least we'll fill up all that void space. So let's try to run it, and we'll do something like this is a test. And you can see now it's sticking those square brackets in there. So it makes it look a little more jumbled up at least. Obviously, this is so easy to break. And then the decrypted message is still correct. This is a test. There's a lot of things you can do here. There's some real famous ciphers that are substitution ciphers like the keyword cipher and the Caesar cipher that you can play around with. You can use random numbers. We'll talk about generating random numbers so that maybe the first time you see a space, you replace it with something, and the second time you replace it with something else. That would just make it a little bit more interesting and hard to break. But there you go. This is an example of using C++'s string class. Very easy. I mean, there's no counting. There's no checking to make sure that things fit. It's handling everything for me. All right, so hopefully your solution is similar. If it's not, you can learn from this one. And if you've got a great solution, you can share it with the rest of the class. I'll see you in the next video.